In this video, we're going to look at another important use of probability distributions. In the 1960s, a researcher worked with two dolphins named Buzz and Doris. He worked with them a long time, teaching them to obey a signal. He put a headlight of a car on the side of their tank, and when the headlight was on, he taught them to come in and push the right-hand button. When the light was blinking, he taught them to push the left-hand button. If they did it correctly, they would get a fish as a reward. So they learned over a period of time how to do that very accurately. Then he made it a little harder. He said they had to put that one dolphin would have to push the button and then the other. Buzz would have to push his first, and then Doris pushed hers. If they did it in the correct order, then they would both get a fish. So they practiced that for a long time until they learned that very well. Then he was ready to start the experiment. He wanted to know, are dolphins able to communicate an abstract thought? Okay, so what he did was he took away Buzz's light, and he put a curtain between the two of them made of canvas so that the dolphins could not see each other. Now Doris knew that if she wanted to get a fish when the light was blinking, Buzz had to push his button before she pushed hers, and the correct button had to be pushed. So Doris knew she had to tell Buzz which button to push if she wanted her fish. So she went over and talked some dolphin to him, making her dolphin noises, and hopefully she was telling him to push the left button. Sure enough, he pushed the left button, and then she pushed her left button and got her fish. It turns out that in one set of trials, Buzz chose the correct button 15 out of 16 times, giving us a sample proportion of 0.9375. There are two possible explanations for Buzz choosing the correct button. One explanation is that he guessed. The other explanation is that Doris told him which one to push. So we want to know which one is the most likely explanation. So this is a very good example of when to use a probability distribution. We looked at using a probability distribution to see how likely we were to win a certain amount of money in a game of chance. However, using probability distributions to make a decision about a statistical problem is a much more useful reason to use much more useful way to use a probability distribution in statistics. So what we're going to do is to look at a probability distribution to see how likely an event is to occur just by random chance. If Buzz was just guessing, he has a 0.5 probability of choosing the correct button. So probability that he's correct here is equal to 0.5. If Doris told him what to do, we would expect him to guess the probability to be significantly greater than 0.5. We can use simulation to create a chance model, a probability distribution for the number of correct guesses out of 16, and use that to evaluate how likely it was that Buzz was just guessing. So in other words, the chance model is the model saying he was just guessing. Okay, so how are we going to do that? We're going to first of all, compute the statistic from the observed sample data. And we got 15 out of 16 was the statistic that we got from the result of the experiment. Then we're going to identify a by chance alone explanation. So the by chance alone explanation was that he had a 50-50 chance of guessing, and he guessed correctly 15 times. Then we're going to do a simulation to see how likely that is to occur. So what we did in class was this. We let x equals 1 represent a correct guess, x equals 0 represent an incorrect guess, and we used random int 0, 1, 16 to simulate 16 random guesses. And then we kept track of how many correct guesses, and that we did this actually really easily by doing the sum of all of this. If we do the sum of this whole process, then the sum would equal the number of correct guesses, because the correct guesses were equal to 1 and the incorrect guesses were equal to 0. So adding up the sum of all those numbers would give us the number of correct guesses. Kind of a little clever thing I learned how to do from another teacher. So when we did our simulation, we did quite a few trials quickly using all of our calculators and combining our results. This is the probability distribution that we got. The bar represents from 3 to 4 represents 3 correct guesses, from 4 to 5 is 4 correct guesses, and so forth. So this bar right here represents 13 correct guesses. Notice that we didn't ever get 14 or 15 correct guesses out of 16, even though we did the simulation 140 times. So you can see here the probability, for example, getting 8 correct guesses is about 25%. The probability of getting 13 correct guesses is about maybe 2-3%. The probability of getting 15 out of 16 in our simulation, 0. Okay, so this then allows us to evaluate which one of our scenarios is more likely. So looking at what's called strength of evidence, we consider whether the value of the observed statistic from the research study is unlikely to occur if the chance model is true. If we decide the observed statistic is unlikely to occur by chance alone, and it is certainly unlikely, we didn't even ever get it one time, then we can conclude that the observed data provides strong evidence against the plausibility of the chance model. In other words, it is not likely that Buzz was just guessing. So this is the one actually that we came up with. It is not likely that Buzz was just guessing, because the probability of 15 out of 16 equals 0 in our chance model. Now, what if Buzz had only guessed maybe 11 out of 16? Okay, so if he had guessed 11 out of 16, that happened 6% of the time. We would have said, okay, it is somewhat unusual, but it is still possible to randomly guess 6 out of 16 times. So, in other words, Buzz's 6 out of 16 or 11 out of 16 could have happened just by random chance. So we wouldn't have strong evidence to reject the chance model with 11 out of 16. But with 15 out of 16, we have strong evidence to reject the chance model. So if we reject the chance model that he just guessed, the other explanation is that Doris told him what to do. So we have strong evidence that the dolphins were actually communicating. Now, to follow up this is kind of an interesting study. To follow this up, then the researcher put a wooden wall in between the dolphins. So he had, this was a wooden barrier, and we had, Buzz over here and Doris over here. And in that situation, Buzz only guessed correctly, I think it was 16 out of 28 times. Now, you can imagine if you did a simulation with 16 out of 28 that you were going to get that it could happen by chance. And so the researcher was kind of confused. Maybe was the wooden barrier too thick and it was hard for them to communicate. Maybe the first thing with the 15 out of 16 was just a fluke and they really couldn't communicate. But then after some further investigation, he found out when he did this first experiment with the wooden barrier, 2 things weren't working. The light signal, Doris's light signal, was not working correctly, and the fish dispenser that gave them the rewards for doing the correct thing was not working correctly either. So it turned out Buzz was just randomly guessing because the whole experiment wasn't working correctly. So when he corrected the light and the fish dispenser and put the wooden barrier in again, he got much more convincing results. He ended up once again with strong evidence that the dolphins were actually communicating. So this is a really interesting study showing how a probability model is used to make a statistical decision, and this is something we will be doing throughout the rest of the year.